In this video, we'll be going through the 2016 Scholarship Physics exam. Question 1. A pair of parallel conducting metal rails are connected to a voltage source as shown in the diagram. The fixed rails slope down at an angle phi to the horizontal between the poles of the large magnet. The force on the current carrying conductor in the magnetic field is given by F is equal to BIL. The voltage induced when the inductor moves through the magnetic field is given by V is equal to BVL. Both of these relationships apply where the magnetic field and the conductor are at right angles to each other, and when the velocity is at right angles to both. Show that a conducting roller can be placed across the rails and remain stationary in the position shown above, if the magnetic field strength is given by that equation there, where m is the mass of the roller and I is the current through the roller and L is the separation of the rails. Okay, so in order for the roller to remain stationary, there must be no net force and therefore there's no acceleration due to F is equal to ma. Therefore, the magnetic force up the rails must be equal to the weight force down the rails. Now, as we know, the weight force down the rails is equal to mg sine theta. We know this is the case because this is down an inclined plane. If you don't know where that's derived from, I have a video about the gravitational component down an inclined plane on my channel. You can go check that out. We also know that the magnetic force due to Lenz's law is equal to BIL. Now, as stated in the question, both of these relationships are when the conductor is at right angles to the magnetic field. However, in this case, you can see that it's not at right angles, it's down a slope. So if we draw our magnetic field lines, where this angle right here is our phi, we can see that the magnetic field is B cos phi. So therefore, our force due to Lenz's law is equal to B cos theta IL. And therefore mg sine phi is equal to BIL cos phi. Now rearranging for B, we get mg sine phi is equal to IL cos phi. Now we know that tan phi is equal to sine phi all over cos phi, and therefore B is equal to mg tan phi all over IL. And as you can see, that is the expression we are looking for. The voltage source is now replaced with a small valued resistor of resistance R. The metal roller moves down the rails and enters the magnetic field. It slows down and continues at a constant velocity while inside the magnetic field. Explain why this occurs. So as the roller moves through the magnetic field, it's going to have a voltage induced into it. This voltage will induce a current and therefore produce a magnetic field. The magnetic field is produced in such a way that it opposes the roller's motion. This is Lenz's law. Thus, the magnetic field that is produced is going to interact with the permanent magnetic field, thus slowing the roller down. And therefore, as the roller slows down, the voltage induced will decrease, therefore the current will decrease, and therefore the force due to Lenz's law will also decrease. The force due to Lenz's law will decrease to a point where the force due to Lenz's law and the weight force down the slope are equal. And at this point, as there is no net force, therefore there is no acceleration due to Newton's second law, the roller will move at a constant speed. So we can write that in. The roller will have a voltage induced due to its movement through the magnetic field. This voltage will cause a current to flow. This current will produce a magnetic field. This magnetic field will be produced in such a way to oppose the roller's motion due to Lenz's law. Thus, the magnetic field produced will interfere with the permanent magnetic field, thus slowing the roller down. As the roller slows down, the induced voltage will decrease, thus the current will also decrease. Once the force due to Lenz's law decreases to the point at which it is equal to the weight force down the slope, there is no net force, thus due to Newton's second law, there will be no acceleration, thus the roller will move at a constant velocity. Show that the constant velocity achieved by the roller through the magnetic field is given by that equation there. Okay, so this exact question came up in the 2022 scholarship exam, so you can also check that out if you want. So we know our voltage is equal to BVL, where this little v is our velocity. And as we know, the roller does not move at right angles to the magnetic field. It is going down a slope. So if we draw out our magnetic field, we again see that the component of B is B cos phi. And therefore, our voltage is equal to B cos phi VL. Now for aesthetic purposes only, we can rearrange this. There we go. Now we also know that V is equal to IR, and therefore IR is equal to BVL cos phi. Rearranging this for our current, and we get I is equal to BVL cos phi all over our resistance. Now, as stated in our previous question, our force due to Lenz's law is BIL cos phi. Now, subbing in this equation for our current, we get the force due to Lenz's law is equal to BVL cos phi all over our resistance times by L cos phi. Now, expanding this out, we get the force due to Lenz's law is equal to B squared VL squared cos squared phi all over our resistance. Now again, as this roller is moving at a constant velocity, there is no net force, and therefore the weight force down the slope must be equal to the force due to Lenz's law up the slope, and therefore our FL is equal to FW. Now our weight force is still equal to mg sine phi, and therefore mg sine phi is equal to b squared VL squared cos squared phi all over our resistance. Now rearranging this for our velocity, we get mgr sine phi all over b squared L squared cos squared phi is equal to our velocity. Now we know that tan phi is equal to sine phi all over cos phi, and therefore mgr tan phi all over b squared L squared cos phi is equal to our velocity. And there you go. That is the equation that we are looking for. Again, this is the exact same question as in the 2022 scholarship exam. With the rails now horizontal, they are connected to an AC 50 Hz power supply, as shown in the diagram. When the switch is closed, the motion of the roller may be any one of a variety of different motions. Explain how this is possible. So in a magnetic field, we know the velocity is directly proportional to the voltage. So in this case, as this is an AC power supply, depending on the phase of the power supply, the voltage is going to vary, and therefore the velocity is going to vary. And so we can write that in our answer. The movement of the roller depends on the phase of the AC power supply. The key idea for this question is that an AC power supply will go through like a sine graph type of thing, where it rises from 0 to its peak value, and it will drop down from its peak to 0, and then fall down from 0 to its negative peak, and then rise from its negative peak to 0, and the cycle continues once more. And these are the different phases of the voltage. We can split it off into 4 quarters, like so, and each phase will have a different movement. As you can see, these two phases right here are the same, just in opposite directions, and these two phases right here are also the same, also in opposite directions. And so in my answer, I will also relate to these different phases. As the AC voltage rises from 0 to its peak, the roller will experience a series of jerks in one direction, due to the increasing current and therefore increasing force. If the frequency is high enough, the motion will appear to be continuous rather than jerky. When the voltage decreases from 0 to its negative peak, the current is reversed and the roller will move in the opposite direction, with the same set of scenarios as in the other direction. However, if the voltage is falling from its peak to 0 or increasing from its negative peak to 0, the roller will be seen to vibrate in place. This is because the force generated on the roller by the magnetic field is very small and therefore not sufficient to overcome any friction or the rotational inertia of the roller. Okay, question 2. Long wires stretched between 2 points can vibrate when steady wind blows past them. Engineers, in dealing with problems caused by these vibrations, have found it useful to define the name I can't pronounce number, which is abbreviated as ST. ST is given by that equation there, where F is the frequency of the vibration, and R is the radius of the wire, and VW is the wind speed. Show that ST is dimensionless. So we know that frequency is 1 over the period, and we know that period is in seconds, and therefore dimensionally frequency is s to the minus 1. The dimension for radius is in meters, and the dimension for the wind speed is going to be meters per second. And therefore st dimensionally is s to the minus 1 all over meters per second. And as you can see, this is going to be ms minus 1 all over ms minus 1, which is going to be equal to 1. And therefore st is dimensionless. A steady wind of 10 meters per second causes the cables to vibrate with a frequency of 200 Hz. In this situation, st is 0.2. The wave speed of the wire is given by that equation there, where T is the tension and mu is the mass per unit length. Explain using physics principles why the wave speed in the wire depends on the tension and the mass per unit length. Okay, so first off, the tension is the force in which the particles experience, and therefore, due to Newton's second law, if the particles experience a force, they are going to accelerate, and therefore move faster, and therefore the wave will move faster, so the wave speed increases. Also, if the mass per unit length decreases, that means that per unit of length, there's going to be less mass, and therefore, due to Newton's second law again, there's going to be more acceleration, and therefore the wave speed will increase again. And so we can write that in. Tension is the force which acts on the particles, thus if tension increases, then due to Newton's second law, the mass on the wire will experience a greater acceleration, thus causing the wave speed to increase. Also, if the mass per unit length is lower, this will cause greater acceleration, thus leading to a greater wave speed. Therefore, due to these two factors, the velocity of the wave is directly proportional to the square root of the tension, and the velocity of the wave is inversely proportional to the square root of mass per unit length. The cradle has a mass of 100 kgs, and the window washer, who is standing in the middle of the cradle, has a mass of 75 kgs. Given that the density of the cable material is 8,000 kgs per meters cubed, show that the wave speed in the cables is 18 meters per second. Okay, so first we need to find the tension in one of the cables. We know that tension is a force, and the force acting on these cables is going to be the weight force. So we know that T is equal to mg, and therefore our T is equal to the total mass, which is 100 plus 75 kgs. So that's 175 kgs times g, which is 9.81. Because there are two cables, this total weight force is distributed between those two cables. As we only want the tension force of one cable, we can divide this by 2. The key information here that allows us to divide it by 2 is that the window washer is standing in the middle of the cradle, therefore the torques on both sides are equal. And this gives us a tension of 858 newtons. So we know that the equation for wave speed in the cable is tension over mass per unit length, and that's all under a square root. We have our tension value right here. However, we do not have our mass per unit length. In order to find our mass per unit length, we need to do some dimensional analysis. By the definition of mass per unit length, we can deduce that the units for mu, mass per unit length, is going to be kgs per meter. Now, looking at the information that's given to us, we can see that we have the density. The units for density is kgs per meter cubed. And therefore, in order to make this into this, we need to times it by meters squared. As you can see, that will make it equal to kgs per meter. So we know that meters squared is just area, and so we need to find the area of the cable. So if we cut the cable in half, we can find the cross-sectional area of that cable. Now, we know cables are circular, and so the cross-sectional area of the cable is going to be the area of a circle, which is pi r squared. Obviously, pi is pi, so we don't need to find that value, but we need to find the radius. We know that st is equal to f r all over vw, and therefore we can rearrange for r, and we get r is equal to st times vw all over the frequency. We know that st is 0.2 as it's given up here. We know the frequency is 200 Hz, And we know that Vw is the wind speed, and this is given as 10. Therefore, plugging in these numbers, we get a radius of 0.01 meters. And therefore, we can find our area, which is pi, and our radius squared, which is 0.01 squared. And that gives us an area of 3.14 times 10 to the negative 4 meters squared. Okay, so we now know that our mu is equal to our density times our area, and therefore mu is equal to 8 times 10 to the 3 times 3.14 times 10 to the negative 4. And therefore this gives us a value for mu as 2.51 kgs per meter. And therefore, as we know, our velocity is equal to t over mu. This means that the velocity is equal to the square root of 858 all over 2.51, and this gives us a velocity of 18 meters per second. And that is the value that we are looking for. There we go. The window washer moves from the center of the cradle to a position 1 meter from the center. Compare the wavelengths of the vibrations in the two cables. Okay, so now we have a case where we have our cables coming down and we have our little platform. Now the window washer right here is now 1 meter from the center, and therefore this distance right here is going to be 3 meters, as the total length is 4 meters. Now explaining this in words, because the window washer is moved slightly towards this side right here, the tension in this rope will increase, and therefore as V is equal to the square root of tension over mu, if tension increases, then the wave velocity must also increase. As V is equal to F lambda, and frequency is constant because St is equal to F R all over Vw. Because St remains constant, therefore frequency must remain constant, and therefore if the wave velocity increases, then the wavelength is the only thing that can also increase. And so, if the window washer moves 1 meter towards this side, that means the wavelength in this cable will increase. Now it tells us to compare the wavelengths, so what it wants us to do is to calculate the wavelengths for this cable right here, and this cable right here, and see which one is larger. Now the way we can do this is by taking the torques of both cables, and so let's get into the question. So let's first label this side as T1 and this side as T2. Right, so we know that T1 plus T2 must equal to the total weight force. We know that the mass is 175 times G, which is 9.81, and this gives us a total weight force of 1,716.75 newtons. As we know, our torque is equal to force times distance, and so from our level 2 we should know that the sum of anti-clockwise torques must equal to the sum of clockwise torques. Now if we set T2 as the pivot, the anti-clockwise torques are going to be going in this direction, and the clockwise torques are going to be going in this direction. And therefore, the anti-clockwise torques is 4T1. The reason for the 4 is because this is 4 meters away, and T1 is obviously the force, and so that would be equal to the torque, right there. And now this is equal to the sum of the clockwise torques. Now the clockwise torques is the weight force of the window washer, the weight force of the cradle as well, and as we know, weight force is equal to the mass times the acceleration due to gravity, and therefore the weight force for the cradle is going to be 100 kgs times 9.81, and we times the distance from the pivot, which is going to be 2 meters, plus the torques produced by the window washer, which is going to be 75 for its mass times 9.81 times the distance from the pivot, which is 3 meters. Now rearranging for T1, we can divide both sides by 4, and this gives us a value of T1 as 1042.31 newtons. Now that we know the value of T1, we can rearrange this equation here for t2 to find the value of t2. And therefore, t2 is equal to 1716.75 minus 1042.31, and that gives us a value of t2 as 674.4375 newtons. There we go. And therefore, the velocity in cable 1 is going to be equal to T1 all over the mass per unit length. The mass per unit length for both T1 and T2 are going to be the same because it's the same cable. And therefore, this is going to be equal to the square root of 1042.75 all over the mass per unit length, which is 2.51. And that gives us a velocity of 20.4 meters per second. Now for cable 2, subbing in our values, we get a velocity of 16.4 meters per second. Now as v is equal to f lambda, therefore the wavelength is equal to the velocity all over the frequency. As both cables have a frequency of 200 Hz as given in previous questions. Therefore, the wavelength in cable 1 is equal to 20.4 all over 200, which gives us a wavelength of 0.102 meters. The wavelength in cable 2 is equal to 16.4 all over 200, and that gives us a wavelength of 0.082 meters. And therefore, as predicted in our discussion earlier, the wavelength for cable 1 is going to be greater. Sweet as. In this scenario, the window washer does not hear beats. Explain the physical conditions required for him to hear beats from the vibrations in the wires when he is standing in the window washing cradle. This is because beats occurs when two waves of similar frequencies superimposed at a fixed point. Due to their slight difference in frequencies, the path difference is not going to remain constant, and therefore you hear a fluctuation of maxima and minima. In this case, the frequency is constant, and therefore he's not going to hear any beats in that case. So we can put that in words. Beats can be heard when two waves of similar frequencies superimposed at a fixed position. Due to their slight differences in frequencies, the path difference does not remain constant, and therefore the window washer will hear a beating sound. However, in this case, the frequency remains constant, thus no beats are heard. A possibility is to alter the radius of one of the wires in order to change the frequency, thus allowing the window washer to hear beats. And that comes from the equation St is equal to Fr all over Vw, assuming that the wind velocity does not change and St remains constant always. If we change the radius, this is going to alter the frequency. And therefore, if we do this in one of the cables, then maybe the window washer will hear beats, because there will be slight differences in the frequencies. So yes. Okay, question 3. A satellite in a circular orbit around Earth has a rotational period of 2 hours. The satellite is orbiting above the equator and is moving in the same rotational direction as the Earth. All satellites at any height are said to be weightless. Explain. So as we know, the satellite is not actually weightless because it still has a weight force being acted on it, but the sensation of weight that you feel every day comes from the reaction force. So if we have a little dude right here, he is standing on the ground, he is going to have a weight force acting downwards like this, but there is going to be an equal and opposite reaction force that is accelerating him up. This is what gives the sensation of weight. However, as satellites are in constant freefall around the Earth, there is no reaction force being acted upon them, and therefore they are considered to be weightless. So let's write that in. The feeling of weight comes from a reaction force. As satellites are in constant freefall around Earth, there is no reaction force, and therefore the satellites feel weightless. Calculate the height of the satellite above the Earth's surface. So we know that our Fg provides our centripetal force, and therefore G big mass times little mass all over our r squared is equal to mv squared over r. We can cancel out our little m's on both sides, and we get G big mass all over r squared is equal to v squared over r. And therefore Gm is equal to v squared r. Now we're going to park this here for now. We know that our velocity is distance over time. Our distance in this case is the circumference of a circle, right? Because the satellite is going in a circular motion. And so the circumference of the circle is 2 pi r. Velocity is equal to 2 pi r all over t, which is just our period. And therefore v squared is equal to 4 pi squared r squared all over t squared. And therefore subbing this in, we get gm is equal to 4 pi squared r squared all over t squared times r. Now we can simplify this by just making this r cubed. Now we're trying to find the height above Earth, so we want to rearrange for our radius. We can cube root both sides in order to get r by itself. And now we can plug in our numbers to get the value of our radius. We know the gravitational constant is 6.67 times 10 to the negative 11 times the big mass, which is just the mass of the Earth, which is 5.98 times 10 to the 24. This is times by our period squared. We know our period is 2 hours, and therefore our period in seconds is 2 times 60 times 60. And that's all squared, and this is all divided by 4 pi squared. And this gives us a radius of 806.0786 meters. Now, slight caveat here, this radius, if we have Earth here, so this is Earth, and then we have our satellite, this radius is from the center of mass of the Earth to the center of mass of the satellite. Now, a key part of this question is above the Earth's surface. And so we only want this distance right here. So we need to minus the radius of the Earth, and we get our desired distance. So if we take 806.0786 minus the radius of the Earth, which is given up here as 6.37 times 10 to the 6, this gives us a value of 1,691 kilometers. There we go. Calculate the angular velocity of the satellite relative to the Earth. So angular velocity, basically how fast the satellite or the Earth is rotating. Now relative velocity, if we have one dude here, and he is traveling at 10 meters per second, and we have this blue dude here, traveling at 8 meters per second, then the relative velocity between these two people are 2 meters per second. Now, if this person was traveling in the opposite direction, at the same 8 meters per second, then the relative velocity between them would be 18 meters per second. So, a key idea here is that the satellite is moving in the same rotational direction as the Earth. And so, we would have the first scenario taking place, where the two individuals are moving in the same direction, and we have a relative velocity of 2 meters per second. Therefore, applying this to this question, we know that velocity is distance over time. Now, subbing in our angular versions of these variables, we know that the angular velocity is equal to theta all over the period, and therefore the angular velocity of the Earth is equal to theta. Now, the angle for one full rotation is 2 pi radians, and therefore theta is 2 pi all over the period, which we know the period of the Earth is 24 hours. Now, making that into seconds, we can times it by 60 twice, and that gives us an angular velocity of 7.3 times 10 to the negative 5 radians per second. Now we can change this to 0.73 times 10 to the negative 4 radians per second. You'll see in a bit why we have done that. Now, taking the angular velocity of the satellite, again it travels a total angle of 2 pi. That's all over the period, as we established before, is 2 times 60 times 60, and that gives us an angular velocity of 8.73 times 10 to the negative 4 radians per second. And therefore the relative frequency is equal to 8.73 times 10 to the negative 4 minus 0.73 times 10 to the negative 4, and that's equal to 8.00 times 10 to the negative 4 radians per second. So the reason why we changed this to times 10 to the negative 4 is just to make this calculation a lot easier. then again, you could just put it in your calculator and it'll give you the same result. Calculate the angle measured with respect to the center of the Earth through which the satellite will be visible to the observer at the equator. So again, if we have our Earth right here, and we have Earth's center right there, because we're measuring with respect to the center of the Earth, there is going to be an orbital radius of the satellite, which is this dotted line right here. And therefore, if someone stands at the equator, there is going to be a certain angle at which they can see the satellite. This is going to be angle theta, and this is also going to be angle theta. And so once the satellite moves past this point right here, the person will no longer be able to see the satellite. And so we're trying to find what that angle is. As you can see here, we have a right angle triangle. As we know, this is the radius of the Earth on both sides, and we can call this distance h. And therefore, this distance is also r. And so if we extrapolate that right angle triangle, we would have r plus h and r over here. And therefore, our theta is going to be the inverse cos r all over r plus h. Now subbing in our values, we know the radius of the Earth, which is given to us, which is 6.37 times 10 to the 6, and that's all over 6.37 times 10 to the 6, plus h, which we found in a previous question, which is this value right here. Right, that's 1691 times 10 to the 3, as that is in kilometers, so we need to put it to the times 10 to the negative 3 to put it back into meters. And that gives us an angle of 38 degrees. Now, as you can see, the observer will be able to see all throughout this angle and all throughout this angle. And so the total observable angle will be 2 theta, which is equal to 76 degrees. And that is the total angle at which the observer will be able to see the satellite. There are limits to the largest and smallest periods of an Earth satellite. Discuss this statement. So we know that t squared is directly proportional to radius cubed, and therefore the limits of the period will be determined by how close the satellite is to Earth, and also how far the satellite is to Earth. So obviously, the further away the satellite is to Earth, the radius will be larger, and therefore the period will be larger, and the inverse is also true. And so basically we can write that in words. The minimum period is determined by how close the satellite can be to Earth without entering its atmosphere, right? If it enters its atmosphere, then it's no longer orbiting Earth, and it's inside Earth now. The maximum period is determined by how far the satellite is to Earth. The gravitational strength will decrease until it becomes smaller than other celestial bodies, and therefore it will no longer orbit Earth. Sweet as. Okay, question 4. A radium nucleus, initially at rest, undergoes alpha decay according to the following equation. Show that the energy liberated is 4.88 mega electron volts. Okay, so first we need to figure out the mass deficit. In order to do this, we take the mass before and we minus it by the mass after. This way we see the difference in mass, and this is our mass deficit. So the mass before is 226.025410 times our U, which is 1.66 times 10 to the negative 27, and that's minus 222.017578 plus 4.002603, and that's all times 1.66 times 10 to the negative 27 also. And that gives us a mass deficit of 8.68 times 10 to the negative 30 kgs. There we go. Now we know E is equal to mc squared, and therefore our energy is equal to the mass deficit times the speed of light squared, and that gives us a energy of 7.8 times 10 to the negative 13 joules. So now we can take this total energy and we can divide it by the charge of an electron to get the answer in electron volts. And that gives us a value of 4.88 mega electron volts, which is the value that we are trying to find. Using appropriate conservation laws, calculate the kinetic energy of the alpha particle and explain why most of the energy released in the decay goes to the lighter particle. Okay, so assuming that all energy goes into kinetic energy, we can say our energy total is equal to the kinetic energy of the radium particle plus the kinetic energy of the alpha particle. And therefore, as we know, our EK is equal to half mv squared, our ET is equal to half mr, which is the mass of the radium particle, times vr squared, which is the velocity of the radium particle, plus half m alpha, mass of the alpha particle, times v alpha squared, which is the velocity of the alpha particle. So this is our conservation of energy equation. Moving on to our conservation of momentum, we know that mr vr is equal to m alpha v alpha, and therefore vr is equal to m alpha v alpha all over mr. Now we can make that substitution into here, and we get our energy total is equal to half mr times mass of the alpha particle, velocity of the alpha particle all over mr, and that's squared, plus half m alpha v alpha squared. Now we can expand this out like so. We get m alpha v alpha squared all over mr squared, and now we can cancel out the power, and we can also times both sides by 2, so we get 2et is equal to m alpha v alpha squared all over mr plus m alpha v alpha squared. Now we can simplify this top part out and make it m alpha squared v alpha squared. As you can see, we have v alpha squared as a common factor, so we can take it out, and we get 2et is equal to v alpha squared m alpha squared all over mr plus m alpha. Now we can divide both sides by this section right here, and we get 2et all over m alpha squared all over mr plus m alpha is equal to v alpha squared. Now we can square root both sides to get rid of this power, and now we have the equation for the velocity of the alpha particle. In the previous question, we found out that our energy total is equal to 7.8 times 10 to the negative 13. And we also have the mass of the alpha particle and the mass of the radium particle as given up here. So plugging in those numbers in, we get a velocity of 1.52 times 10 to the 7 meters per second. Now, again, as we know, EK is equal to half mv squared. The EK of the alpha particle is equal to half times the mass of the alpha particle times the velocity of the alpha particle squared. And subbing in our values, this gives us a value of 7.67 times 10 to the negative 13 joules. Now dividing that by the charge of an electron in order to get the value in electron volts, this gives us a value of 4.79 mega electron volts. Okay, so this question also asks us to explain why most of the energy release goes into the lighter particle. So let's explain that right now. The alpha particle, which is the lighter particle, has most of the energy as it has the higher velocity. This is because velocity is squared in the EK equation. This compensates for its smaller mass. Thus, the alpha particle carries 98% of the energy. We get this 98% because we have 4.79 all over 4.88. This is the total energy, and this is the energy of the alpha particle. And this gives us 0.98, which is 98%. There we go. The graph to the right shows the range of kinetic energies observed in the electrons released in the typical beta decay. There is a distribution that cuts off at some maximum kinetic energy. Initially, researchers concluded that the products of beta decay were simply the daughter nucleus of a fast-moving electron's beta particle. Wolfgang Pauli, I think that's how you pronounce his name, used the above graph to conclude that there were some additional particle involved in the beta decay. Explain how this conclusion can be reached. So this question is basically talking about how before the neutrino was discovered, scientists were baffled with how this graph looked, because you would expect that the proton will move off this way and the electron will move off in this direction. However, this is not the case, and the electron actually veers off to the side a bit, meaning there's a much smaller particle coming off like this. That's conservation of momentum for you. And the reason why we know this is a much smaller particle, just like in the above equation, the lighter particle stole most of the kinetic energy, we can see by this distribution of this graph, there is a particle stealing some of the kinetic energy of the electron. And so this lighter particle is the neutrino or the neutron, and that was added to the beta decay equation. So we can write that in. For every decay, you should expect the same energy liberated each time. However, as seen in the graph, this is not the case. Thus, as there is a distribution of energies, this implies that there is another, smaller particle that has the missing energy. The rest mass of a deuteron is that monstrosity right there. If the proton and neutron are separated, then the sum of the rest masses is that monstrosity there, i.e. more than the original value. By contrast, if a rocket ship separates itself from a planet by burning fuel to escape the gravitational pull, then the total mass of the rocket on the launch pad is significantly more than the mass of the rocket after escape. Compare and contrast these situations. Okay, so the rocket will eject its mass in the form of rocket fuel in order to escape the gravitational pull and go into the atmosphere. However, a deuteron requires energy in order to separate the proton and the neutron, and due to the mass-energy equivalence, this added energy manifests itself into added mass. And so that's why the mass before is greater than the mass afterwards. So we can write that in. The deuteron requires energy to separate the proton and the neutron. This added energy manifests itself as mass due to the mass-energy equivalence. However, the rocket ejects its mass, which is rocket fuel, in the form of internal energy in order to gain gravitational potential energy and kinetic energy. Okay, question 5. The diagram shows two masses, M1 and M2, initially at rest, connected by a rigid massless rod of length k. Initially, M1 is located at the origin, and M2 is located at coordinates 0k. Two additional masses, M3 and M4, travel towards the rod at speed v and 2v respectively. Mass M3 strikes M1 at the same time as mass 4 strikes M2, and they both stick together respective of their targets after the collision. M1, M3, and M4 all have the same mass m, while M2 has a mass of 2m. Show that the coordinates of the center of mass of the system immediately after the collision is that right there. Okay, so we know that the center of mass equation is equal to m1x1 plus m2x2 all over m1 plus m2. Now if we analyze this situation after the masses have collided, we will have m2 right here and m4 right here. This will be m1 and this will be m3. Now we know that this distance is k, right here, k, and we know that m1, m3, and m4 all have a mass of m, while m2 has a mass of 2m, thus this mass up here is 3m, and this mass down here is 2m. Now in order to calculate our center of mass, we need to set an origin point. If we set m1 as the origin, this means that x1 will equal to 0. Thus, as x1 is equal to 0, this term cancels out, and our x center of mass equation becomes m2x2 all over m1 plus m2. And therefore, plugging in our variables, we get the center of mass is equal to m2, which is this mass right here, which is equal to 3m, plus x2, which is the distance from the origin, which is length k, so 3mk, all over m1 plus m2. m1 is 2m, m2 is 3m, and this gives us 5m in total. As you can see, the m's will cancel out, and this gives us a center of mass of 3k all over 5. Therefore, the center of mass will be somewhere over here. Now if we look at this point on our diagram, that will be somewhere over here. As you can see, in the x direction, this is still 0, but in the y direction, this is our 3k over 5. Now, as you can see, this is the coordinate that we're trying to find. There we go. Show that after the collision, the rotational inertia of the system about the axis perpendicular to the x and y plane passing through the center of mass is given by that equation there. So we know I is equal to mr squared, and our I total is equal to I1 plus I2. Now if we look at our diagram again, draw this out, we have our two masses. This has a total mass of 3m, and this has a total mass of 2m. Our center of mass is somewhere over here. We know that this distance right here is 3k over 5, and therefore this distance over here must be 2k over 5. So if we define this side as our I1 and this side as our I2, our I1 is going to equal the mass, which is 2m, times our radius squared. Now our radius with respect to the center of mass is 3k over 5, and that's squared. Now expanding this out, this gives us a value of I1 as 18mk squared all over 25. Now our I2 is equal to the mass, which is 3m, times our radius, which is 2k over 5. And that's all squared. Expanding this out, this gives us a value of 12mk squared all over 25. Again, our I total is equal to I1 plus I2, therefore that's 18mk squared all over 25 plus 12mk squared all over 25. Now as they have the same denominator, we can just add the numerators together, and this gives us I total as 30mk squared all over 25. Now as you can see, the top and bottom can both be divided by 5, and therefore I total is equal to 6mk squared all over our 5. And as you can see, that is the equation that we're trying to find. Sweet as. Calculate the angular velocity of the system after the collision about the same axis defined in part B. Okay, so in order to calculate the angular velocity, we can use our conservation of angular momentum. As we know, angular momentum is equal to mvr. Now as you can see, mass m3 and mass m4 are the only masses that are moving before the collision, and so those are the only masses that will carry angular momentum. So the angular momentum of mass 3 is going to be m, which we know that mass 3 has a mass of just 1m. Remember, mass 2 is the only mass with 2m as its mass value. It has a velocity of v, and the radius, when it collides, is going to be this distance here, which we know from up here is our 3k over 5. Similar thing for the angular momentum of mass 4. It has a mass of 1m, however it has a velocity of 2v and a radius of 2k over 5. Now our angular momentum initially is going to be the angular momentum of L3 plus L4, and therefore initially mv3k over 5 plus 2mv 2k over 5. This can be simplified to 3mvk all over 5 plus 4mvk all over 5, and this gives us an angular momentum initially of 7mvk all over 5, or 7 over 5 mvk. That's the same thing, just rewritten. So we know, due to conservation of angular momentum initially must equal to angular momentum finally. We also know that angular momentum is equal to the rotational inertia times the angular velocity. Therefore, as we know, our initial angular momentum is 7 over 5 mvk, and that's equal to the angular momentum finally, which as we know is equal to I omega. Our I finally is the value that we found in the previous question, which is 6 over 5 mk squared times our angular velocity. Now remember, this angular velocity is the value that we're trying to find, so we can divide both sides by 6 over 5 mk squared, cancelling out our masses and cancelling out the power for the k. We get 35v all over 30k is equal to our angular velocity. Simplifying this down by dividing both the top and bottom by 5, we get 7v all over 6k is equal to our angular velocity, and that is the final equation. If m is 2 kgs and v is 2 meters per second and k is 1 meter, calculate the coordinates of the combined mass m2 plus m4 at time 0.5 seconds after the collision. Okay, so there's two parts to this question. The first part is both mass m2 and m4 are going to move themselves, so the coordinates of those masses are going to move, plus the coordinates of the center of mass is going to move. So if the coordinates of the center of mass moves, then we need to add this to the coordinates of mass m2 and m4, and that will give us the final coordinates. So if we look at our diagram over here, m2 and m4 is this top part, so if we look at it after the collision, right here, this is going to be m2 and m4, so we need to find the new coordinates of those masses. For simplicity's sake, I'm going to draw them as one mass, so it's easy to draw. When they collide, there's going to be a force applied here and a force applied here. As you can imagine, this is going to cause the dumbbell to rotate, like so, and there's going to be an angle right here, which we can call theta. Right, so this is rotation right here. Now doing some trigonometry, we can define a right angle triangle right there, where this is our right angle. Now in order to find that angle, we know that omega is equal to theta over t, and therefore theta is equal to omega t. Our omega, which we found in the previous question, is equal to 7v over 6k, and our time is given to us as 0.5 seconds. Therefore, our theta is equal to 7v over 6k times 0.5. Our velocity and our k are given to us, so we can sub those values in. 7 times 2, which is just 14, all over 6 times 1, which is just 6 times 0.5. This gives us a theta of 1.167 radians. Or we can put it in a fraction form as 7 over 6 radians. The reason for the fraction is because this is more accurate, and so when we're doing our calculations, we don't get a rounding error. So looking at our trigonometry now, we know this distance here is 2k over 5. We've seen that many times. And therefore, this distance right here must be 2k over 5 sine theta. And this distance right here must be 2k over 5 cos theta. And therefore, as you can see, relative to the center of mass, the masses m2 and m4 have moved on the x-axis by a distance of 2k over 5 sine theta, and on the y-axis of 2k over 5 cos theta. And therefore, our new coordinates are given as 2k over 5 sine theta and 2k over 5 cos theta, right? This is our x and this is our y. Plugging in our values, we know that k is just 1, so that's 2 over 5 sine theta, which is 7 over 6, and our y is again 2 over 5 cos 7 over 6. Now plugging this in our calculator, this gives us a coordinate of negative 0.3678 and a y coordinate of 0.1573. So that is the new coordinates of the mass m2 and m4 after the collision. But as discussed previously, the center of mass is also going to move, so we need to take that into account also, and then we can find the true new coordinate of mass m2 and m4. So in order to do this, we can use our conservation of momentum. So therefore our pi is equal to our pf. Now we can define to the right as positive and to the left as negative, and therefore m3v3, so that's velocity of m3, minus m4v4 is our momentum initially. Again, the reason for the minus is because m4 moves this way, which we have defined as negative. And so that is our initial momentum. Now we can plug in our values. We know that m3 is just mass m, and m3 is moving at a velocity v, minus m4, which again has a mass m, but is moving at a velocity of 2v. And so this is our initial momentum, so mv minus m2v. Now our final momentum is 5mvf. Vf is the final velocity. This 5m comes from the fact that after the collision, the top is equal to 3m and the bottom is equal to 2m. So all of it combined is obviously equal to 5m. We don't know the final velocity, but we can use that final velocity to find the new location of the center of mass. Rearranging this to make it easier for our calculations, we can say that mv minus 2mv is equal to 5mvf. And therefore, negative mv is equal to 5mvf. Dividing both sides by 5m, we get negative mv all over 5m is equal to vf. We can cancel out the masses, and we get negative v over 5 is equal to vf. We know that our v is equal to 2 meters per second, so we can make that substitution. Negative 2 over 5 is equal to vf. And therefore, negative 0.4 meters per second is our vf. So we know that the original location of the center of mass is 0.3k over 5. Now we know that k is equal to 1, and therefore the original location of the center of mass is 0.6. Again, this is the x and this is the y. One thing to note is that the y coordinate of the center of mass will not change because the masses are being hit at the horizontal, and so only the horizontal distance of the center of mass will change. Now, as we know, velocity is equal to distance over time, and therefore distance is velocity times time. And therefore, the new location of the center of mass is going to be vft times 0.6, again, because the y coordinate does not change. And therefore, subbing in our values, vf is negative 0.4 times our time, which is 0.5, and the y coordinate is 0.6. This gives us a new coordinate for the center of mass as negative 0.2, 0.6. And now we can add those new coordinates to these coordinates right here to get the final coordinates of masses m2 and m4. So we can plus our negative 0.2 and then plus our 0.6, and we get coordinates of negative 0.5678 and negative 7573. And that is our final answer.